Hi everyone, my name is Sungmin and I'm currently with Gwangju Institute of Science and Technology. It is my great pleasure to have a presentation in the SISPAD 2020 Workshop 1 Combination of TCAD and Machine Learning. The title of my talk today is Neural Networks for the Solution of the Poisson Equation. In this presentation, I want to discuss about our approach to accelerate the TCAD simulation with the help of a neural network. This is the acknowledgement. Financial support from the National Research Foundation of Korea is gratefully acknowledged. And I personally thanks to my student Mr. Seung-Chul Han and my colleague Professor Jong-Hyun Choi. This is the outline. In the introduction, the motivation of this work is presented. Recent research reports on the combination of the TCAD and the machine learning are briefly reviewed. In the second part, approaches to solve the Poisson equation are reviewed. Next, our approach to learn the numerical solution is described. Achievements and issues are presented and our plan for further improvement is sketched. After that, the conclusion is made. Introduction. Let me get started with our previous conference, SISPAD 2019, Udine, Italy. There were a few papers on the machine learning. They are listed below. Since then, 1 year has been passed. How about the SISPAD 2020? Now we have a session entirely devoted to the machine learning, session 15. And there are more papers which are not included in the session 15. The number of papers is sharply increasing. Moreover, this workshop 1 combination of TCAD and machine learning itself clearly reveals that our community is currently very much interested with the keyword machine learning. However, although we are interested with the keyword machine learning, the actual research activities are quite diverse. The machine learning is not an application field, but a technique to solve problems. In next slides, I wanted to briefly review some papers presented in recent SISPAD events. The first one is from Singapore, National University of Singapore. In this paper, the application field is the failure analysis. More specifically, the failure due to tinitride breaching defects is analyzed. First, the TCAD simulation is performed for structure with a breaching defect to generate the IV curve. The goal is to estimate the position of the breaching defect from a given IV curve. Some features such as the subthreshold swing and the threshold voltage are used in the supervised learning algorithm based on the random forest. The second example is from San Jose State University. In this work, a one-dimensional PIN diode is considered. Variation of the IV curve due to the thickness doping variation is simulated. After that, by using the linear regression technique, the thickness and the doping density are predicted and compared with the actual values. In SISPAD 2018, Samsung reported their efforts in the Design Technology Co-Optimization DTCO. They used a neural network in the yield estimation flow. The neural network would provide an efficient way to relate the technology parameters and the failure criteria. The Monte Carlo technique is applied to realize a large number of samples. Up to now, we have reviewed some recent works. As we can see clearly, in those works, First, the TCAD simulation is performed as usual. After that, the simulation results are used to train a machine. Once after the machine is sufficiently trained, instead of time-consuming TCAD, the trained machine is used. It is noted that the TCAD simulator is treated as a given program. As a TCAD developer, I thought that we can improve this situation. The TCAD simulator itself can be a target application of our machine learning technique. We have tried to find out similar approaches, but not very successful. One plausible exception can be found in the process simulation. In this work, the fin shape is predicted by the neural network. When the quality of the fin shape generated by the neural network is not sufficiently high, then the neural network is further improved. Eventually, we will have a neural network which can predict a fin shape quite close to the realistic one. It is a very interesting idea, however, it is not applied to the device simulation. Our motivation is shown in this slide. When the TCAD is involved in the technology development, the entire TCAD simulation cycle repeats with the new experimental result until the development is finished. Therefore, we have to simulate similar devices with modified parameters again and again. Consider an extreme situation where we have to simulate the same device twice. Even in this case, our second simulation run takes the same amount of time with the first run. We hope that a neural network can provide a means to improve the efficiency. The idea is quite simple. Since we are solving a set of nonlinear equations, an initial guess for the Newton method should be provided. If we can provide a good initial guess, the number of Newton iterations can be reduced significantly. Especially, although we are interested with some particular bias points for I up and I on, a time-consuming bias lamping should be made to reach the target bias. In an ideal case, the speed-up factor is expected to be about the number of intermediate bias points toward the target bias. Now, our ultimate goal is as follows. The structure file and the target bias condition are used as input parameters. From these input parameters, the neural network generates a good initial guess at the target bias condition. Then, the conventional device simulator takes this initial guess to start the simulation. Of course, this is our ultimate goal. At the beginning, a fixed bias is considered. It should be generalized later. Then, how can we generate a good initial guess by using a neural network? There may be two different approaches. The first one is to build a neural network which can solve a differential equation. For example, we can think about a neural network for the nonlinear Poisson equation. For this approach, in the part 2, I will leave you some related works. The second approach is to build a neural network which learns numerical solutions without understanding the differential equation. For this approach, in the part 3, our SISPAD2019 paper will be revisited. In this part, neural networks to solve the Poisson equation are reviewed. Why do we consider the Poisson equation? It is simply because the Poisson equation plays a fundamental role in the device simulation. From the net charge distribution, the electrostatic potential is calculated by the Poisson equation. The electrostatic potential is used to determine the charge densities. In a workshop of NIPS 2018, a paper about the Laplace equation was presented. The Laplace equation is obtained when the source term of the Poisson equation vanishes. A fully connected neural network is trained to minimize the loss function. The authors assume a specific structure and the mixed boundary condition is applied. For two contexts, we have 1 or -1, and for other non-contact boundaries, the homogeneous Neumann boundary condition is applied. Similar boundary conditions are found in the semiconductor device simulation. The adopted network structure is shown here. A fully connected network with certain depth and width is shown. As you can see, the input parameters are just x and y coordinates, and the output is the solution of the Laplace equation. The sampling points are randomly selected. It is noted that the width parameter is quite small, like 8 to 40. Another attempt to solve the Poisson equation is suggested by a group in the Imperial College London. The Poisson equation with the Dirichlet boundary condition is considered. It is decomposed into two equations. One is the Poisson equation with the homogeneous Neumann boundary condition. The other one is the Laplace equation with the Dirichlet boundary condition. The network structure is shown below, and the input parameters are the entire source term and the grid spacing. Also, the output is the solution over the entire simulation domain. When compared with the previously introduced work, its network size is much larger. This large network is trained with randomly generated source terms. Results with the homogeneous Neumann boundary condition are shown. When the source term is given, the trained neural network gives a predicted solution profile. It is compared with the numerical solution. A good agreement is obtained. Up to now, we have briefly reviewed two examples of the Poisson or Laplace solver based on the neural network. They are trained to minimize the loss function directly related with the differential equation. Although it is interesting, application of this approach to semiconductor device simulation has not been reported yet, to the best of my knowledge. In part 3, our approach to train a neural network directly with numerical solutions is described. It is based on our SISPAD2019 paper. The electrostatic potential is taken as the key quantity. Under a fixed electrostatic potential profile, the electron and hole continuity equations become linear or at most locally nonlinear. Therefore, we can easily get the carrier densities on the fixed potential profile. We assume that a conventional device simulator is easily accessible to us. The numerical solution can be obtained whenever we want to have. In the training phase, the difference between the predicted profile and the numerical solution is used to estimate the loss function. It is different from the approaches in part 2. Once after the training phase is finished, we can use the generated profile. The neural network is built and trained by using Python libraries. An in-house code has been written in C language by Mr. Seung-Chul Han. Each calculation is done in a laptop. At equilibrium, the nonlinear Poisson equation is solved. Simple one-dimensional abrupt p-n diodes with various doping densities are considered. The input parameters are the doping densities, and the output is the electrostatic potential at every grid point. As shown in the right figure, such a shallow neural network is sufficient to represent the solution. However, we have immediately found that it cannot be applied to non-equilibrium cases. We have prepared a new test set, and this slide just shows the structure under simulation. Since a shallow network is not working successfully, we introduce a deeper network. It has 6 hidden layers. The local equilibrium potential is understood. The neural network predicts only the difference between the actual potential profile and the local equilibrium potential. With the deeper network shown in the previous slide, both the bias dependence and the doping dependence can be described. They look good, and more detailed analysis is followed in next slides. We have spent 50 epochs to train the network. In the left figure, the mean absolute error is shown as a function of epoch. The error is rapidly decreasing in initial epochs. Also, the validation set is prepared and tested. The validation error also shows a similar trend. For various doping densities, the error of the electrostatic potential is drawn at a bias of 0.4 volt. The largest error is 15 millivolt, which is quite small. This slide just shows the output values of each hidden layer. Two different bias voltages, forward 0.7 volt and reverse minus 0.7 volt, are considered. Actually, it is difficult to find any underlying principles for those output values. They look completely random. However, at the last hidden layer, the reverse bias case has usually larger values than the forward bias one. In the last hidden layer, the reverse bias case generates larger output values. It affects the final result of the output layer. As shown in the slide, the reverse bias gives much larger variation of the electrostatic potential. When it is added to the local equilibrium potential, we can get a wider depletion region. So, in summary, although we have no idea about its working principle, the neural network is trained to mimic the correct behavior. When the generated potential profile is used as the initial guess, without lamping the bias, non-equilibrium cases can be directly simulated within a few Newton iterations. It is possible because the initial error is already quite small. In this work, we have demonstrated that our simple idea really works. Although not shown in this workshop presentation due to the time limitation, extension to a two-dimensional structure has been made with additional efforts. In my personal opinion, it is interesting and promising. However, in order to be practical, there are many remaining issues. The most serious one is the mesh dependence. Currently, we fix the mesh and change the doping densities. this restriction should be relaxed. Also, the dependence on physical models such as statistics, mobility, generation recombination, and so on should be considered. Therefore, we have a long way ahead. Our short-term plan is to introduce a device template. Instead of trying to build a general solver, we may restrict ourselves to a specific class of devices. For example, in a tool available in nanohub.org, we can generate various BJTs by changing some parameters. I think that it can be a short-term solution. Before finishing this part, it is noted that Mr. Seung-Chul Han has a presentation in the main conference. Its paper ID is 13.5. In this work, two-dimensional bipolar junction transistors are considered. With a CNN, a two-dimensional potential profile is generated. Also, the device template is introduced. You can find much more advanced result in that presentation. Let me conclude my talk. In this presentation, our recent research effort related with TCAD plus machine learning has been presented. We wanted to accelerate the device simulator with the help of a trained neural network. Before introducing our own work, other approaches have been reviewed. Results are demonstrated. And please watch Mr. Han's video 13.5. We should admit that there are many remaining issues. The most serious one seems to be the mesh dependence. For a while, we wanted to avoid it by introducing a device template. Any comments or suggestion for the future improvement is greatly welcome. Thank you for your attention.